In the most recent video I spoke about energy, how it was created at the Big Bang when the matter units separated at the speed of light and with a constant momentum, and therefore you had, of course, a Big Bang. I want to talk now about energy more because we know the momentum did not carry the particles indefinitely away from one another at the speed of light. They turn around when the universe had become extremely large and return and collapsed, and then that's how particles were formed. Ultimately protons and neutrons and electrons, and these combined into a larger number of particles called atoms, which represent the elements, and there are just under 100 of these. So we went from one singularity to 3 nuclear particles, and then to about 100 atoms, different kinds of atoms. And then from there you went to compounds of elements, of which there are millions. So the universe not only became large, but it also became varied, and eventually the compounds formed life, and when there were organic compounds with a lot of carbon and hydrogen and oxygen in, and life was formed, and then of course now we have various forms of life due to the evolution of the living forms. But I want to get on to talk about energy, and I'm going to talk about the equations for energy. And we have 2 equations, or 2 basic equations, because we don't really have an equation for energy, the whole of energy. Energy has 2 phases. You could call it phases, equivalences. It's not really 2 forms. Kinetic and potential energy are just different ways of looking at it. But the equation for kinetic energy that we use is a half the mass times the velocity squared. And if you were watching the last video, you'll notice that I wrote that up and I said half the mass times the volume squared. I blamed that on my tongue. It's a slip of my tongue. My brain said say velocity, but my tongue said volume because it was so used to talking about volume in other areas. So I blamed it on my tongue, not my memory. Or I could say it was a deliberate mistake to see if you were watching, but I'm sure most people noticed it, and a few seconds later I did refer to it as velocity. So I hadn't forgotten, really. I may do it during this program, but it'll be a deliberate mistake. So there's the energy equation for kinetic energy, and we have an equation for, that's kinetic energy, these dimensions of this are force times distance, which is how I defined energy. And in the case of velocity, if you apply a force, say you push a car down a straight road, a flat road, a level road, then you push it to a certain velocity, and it gets a certain kinetic energy. The energy, half mv squared, is equal to the force that you apply. You might be able to apply, say, 100 pounds of force. And if you push it for 10 feet, that's 100 foot-pounds, 10 feet times your force, 10 times 100 is 1,000 foot-pounds of energy, which converts into this. So it's still force times distance. Now another definition of force times distance is what we call potential energy. And that's also force times distance, but in this case it's the force against the spring or force against gravity, that you lift something that has a weight, and you apply a force to overcome that weight, and I lift that 2 feet and say it weighs half a pound. That's 1 foot-pound of energy, exactly the same as the car that you pushed. So energy is energy, whether you call it kinetic energy or potential energy. It's force times distance in both cases. The energy for that, the equation for that, Einstein gave us Newton, of course. Einstein gave us other equations. And Newton's equation was that it was the mass of one body times the mass of another. In this case, the mass of this times the mass of the Earth. In the case of a car, it's the mass of the car times the, although it's not potential energy, you didn't lift the car, but that's the mass of the car. And this is the mass of the Earth, and say this roll of paper. So the product of those two. Why the product of those two? Well, energy is between two units of matter. We saw that with the Big Bang. Single units of matter separated by a distance had a certain energy. But if you have lots of units of matter separated by other lots of units of matter, we call them bodies of mass. This is the number of relationships between individual units of matter. So to get that number of connections, if you had a boat with 100 men and another boat with 200 women, and all the men loved all the women and vice versa, you'd have 100 times 200 relationships. And that's what happens here with the two bodies of the mass. So that's just a multiplication factor. I know mass has dimensions, but really it's just, in this sense, it's just a multiplication factor. And so that's the number of forces, lines of force. And it's that times the universal gravity constant, which I think has is uppercase G, and it's divided by to get Newton's equation for force. You remember that mass times the mass of one body times the mass of the other times, well, this part here times the universal gravity constant divided by the square of the distance. Well, if you integrate that multiply the force by the distance, then you get a single distance underneath. So this is R1 minus 1 over R2. And this is the diameter of the Earth, for example. If I throw this up, the potential energy, when I throw it up at the top of its trajectory, it has more potential energy than it does when it's on the bench. So this is the distance from the bench to the center of the Earth, and that's the distance from its apex of its trajectory. And that's change gives you the potential difference between those two locations. So you'd think, oh, well, this must be the energy here and the energy here. But oddly enough, it is not. And that's because Newton's equation does not give you the energy here or the energy here. It gives you the difference between them. It doesn't say what the energy is here. So if you add or take this energy away from this energy to get the energy difference, you can't do that using Newton's equation. This is not the difference between the energies relative to the center of the Earth. This is the energy from here to an infinite distance in space, the escape velocity, that's where it comes from. If this had enough energy to be able to go up and never come back, that would be that energy. And then if it went from here, it would need less energy to escape. And the difference between those two escape velocities is what gives you the energy from here to here. It's the difference between the energy required to escape to infinitely into space. It's an odd kind of way of doing things. This, of course, these are very, very large numbers, and it's the difference between two very large numbers, or the reciprocals of two very large numbers. But that's the equation. So the dimensions of that are mass times g. Now g has the dimensions of distance cubed divided by mass times time squared. That's what the g is. And now we've got another mass here, another time distance here. So that's the overall dimensions of energy as defined here. And that is force times distance, and that works out to be force times distance too. But I want to draw your attention to something. This is the mass of the Earth, and if you take the mass of the Earth and the mass of the Moon, and you put the mass of the Earth here, the mass of the Earth here, the mass of the Moon here, the distance between the Earth and the Moon, or the average distance, and the same thing here, and the period of the orbit, not in cycles or seconds per cycle, but in seconds per radian, which is the length equal to the radius of the orbit, you'll find that you get for G, we only need one of these to get, well, you just need these three here to get G. You'll find you get exactly the same as the books say, 2.67 times 10 to the minus 11 cubic meters per kilogram per second. So this actually is, and they'll do that for any of the planets on the Sun, all the planets including Pluto. You'll get exactly the same answer. Well, within 3 significant digits, within 0.1%. It's not precise, partly possibly because the radii, the radiuses are not perfect circles, so that the radius is average is not. It's not a perfect circle, so that will give you a difference, and possibly for other reasons too, or the fact that we don't know the masses perfectly or the period. Now, but what I want to point out is this, and that is that if you, well, first thing I'm going to point out, no, I won't. I'll just stick to the subject, and that is that the energy for kinetic energy has only one mass. And this has got 2 masses. Well, you say, well, really it's only one because of this, but then the mass affects the period. And so the mass of the Earth does come into the calculation of potential energy. And we know that. No one's going to quibble about that. So even though they cancel out here, this brings it back in. And I mentioned when I was talking about airplanes that there's no mention here of the mass of the Earth, but the velocity of an airplane, for example, depends on the mass of the Earth. If the Earth were twice as heavy, the plane would have to go about 40% faster to stay up there, because, and the Moon would have to orbit the Earth faster to stay up there because of the more gravity. So the mass of the Earth is there. But I'd like to see an equation where we do include the mass of the both bodies in the kinetic energy. But I won't do that just now. What I'll do now is, I can't do 2 things at once. I can't clean a board and think. Yes, the way in which we add together the kinetic and potential energy to form the total energy, you can't add them those values. You can add the total energies. You could say if the energy is so many foot-pounds for kinetic energy and so many foot-pounds for potential energy, you can add them to get the total energy. But where you have distances, and when the Big Bang occurred, you had distances between and the velocity was constant initially. Well, yes, I'm sure it was constant. But you had a length representing the potential energy, and if you add the potential energy, which is the distance between the 2 bodies, to the kinetic energy by giving the kinetic energy the equivalent length. In other words, if this is potential energy, I won't put it down, I'll put the parenthesis there to show it not that it is the energy, but it is the length that corresponds to it. This is the distance in space between 2 bodies, and the energy is a function of the distance. I'm not going to go into what function it is because I have different opinions on that. But this is the right angle here, and this is the kinetic energy, and this is the separation that gives an equivalent potential energy to the kinetic energy. So now we can express kinetic energy to look like a potential energy, and that gives you a distance that corresponds to the kinetic energy. I call it the energy equivalent length. Add those together as vectors and you get the total energy. And the important thing about conservation, remember I said that energy is conserved, it's this energy that's conserved. This energy between 2 bodies that are not touching anything else, either than one another or anything else, this is a constant. And the moon has had the same constant energy since it left the Earth 4.5 million years ago. But the kinetic energy, potential energy have changed. These can change because they're just different ways of looking at it. They don't really physically exist. I used that expression in an earlier video. This actually is space which really exists, but this here is just a representation. And so this actually doesn't really exist. You could even kind of half knock it out to say it just completes the triangle. You don't need it there because you have two lines and a right angle, which gives you a congruent triangle. That is to say, one that can be repeated exactly the same. You don't need this line. Three lines will give you, three sides will give you a congruent triangle too. But you don't need this line. If you've got the angle because of the difference in representation, you've got the length, the total energy and the potential energy, both represented by distances, and that gives you a definition. But when you say this here can go anywhere between here and here in a semicircle and be and will add up to this. And so that when a body like the moon, or if I throw this up and catch it, that has a different kinetic energy, a different potential energy, but its total energy, what it has here plus what I gave it, that total energy throughout its trajectory did not change. And that actually tells us how gravity works. But that's a long story, and I'll talk about that again some other time. So thank you for watching this.